Okay, so this is section 8.5. Okay, and this is about exponential functions. And sorry, I'm just going to repeat real quickly. If you see like this first table of values here, where as x goes up by 1, from -2 to -1 to 0 to 1 to 2, y goes up by adding 2 to each previous number. If you're adding on the y to get to the next number, it is linear. If on the second table of values, we're going adding 1 there, adding 1 there, adding 1 there, adding 1 there, like we did the other way, but we have to multiply to get to the next number on the y, then this is exponential. And how do we write that function? Okay, and here's how we write this function. It's going to be y equals, or f of x, if we're in function notation, but I believe the book will tell us to write it as y. We want to write this as a formula, as a function. Y equals, okay? So, look at when x is 0 on the second table of values. When x is 0, what is y? 4. Okay? Times. What am I multiplying by? 2. Raised to the x power. And that's the equation that's associated with this table of values. And this is an exponential function. It is not 8 to the x power. It is 4 times 2 to the x power. Okay? Check it out. Let's check it out. Let's say, what would the next number be if I added 3? What would the next number be? Yes. Well, because it is exponential, and I'll show you why. If I were to put 3 on the x, okay, what would y be? 32, and this is y. Watch. Y would equal 4 times 2 raised to the third power, because I made x 3. And what is 2 to the third power? Not 6. It is 2 times 2 times 2, or 8. 4 times 8 is 32, and that would be the next number, wouldn't it? And so that's why it is exponential. Okay? Let's do another one of those. Let's take a table. Maybe I'll do it right on this screen. All right, let's take another one. Let's take where my x is -2, -1, 0, 1, and 2, and the y is 1/4, 1/2, 1, 2, and 4. Okay? Tell me what the equation would look like. Y equals, what would I write here? 1 times, what do I have to multiply to get to the next number? 2. 1 times 2 is 2. 2 times 2 is 4. 2 raised to the x power. The 1 comes from when x is 0. You look at the 1. Okay? That's where the 1 comes from. Where do you get the 2? Whatever you have to multiply by to get to the next number. Yes. Yes, it can. And so 1 times that is just going to be itself anyway. So we can write this as y equals 2 to the x power. All right? So it's not too bad, is it? And that's called exponential functions. All right. It is kind of easy. If we were to graph this function, 2 to the x power, if we were to graph an exponential growth, and that's all we're going to talk about is exponential growth today. What does it look like? Let's take this function here and let's put in values for x, and so we can get an idea of what the graph may look like. We know it's not a straight line. And then I'm going to ask you to tell me what the domain and range is. Let's do the domain and range first. Let's do domain. Can x equal 0? Yeah. In fact, what is 2 to the 0 power? 1. So when x is 0, y is 1. Okay, and that's this point right there. Okay. Can x equal negative numbers? Can we have negative exponents? Yes. We saw that last couple sections, right? When x is negative 1, 2 to the negative 1 is 1/2. When it's negative 2, it's 1/4. So we'd have a point here. We would have a point here. What happens when x is 1? What is y? 2 to the first power. And when x is 2, y is 4. Every exponential growth problem looks like this. So when x is 1, y is 2. When x is 2, y is 4. And so we have this sloping curve that looks like this. And that's what an exponential growth curve looks like. All of them do. The domain in all of these is going to be all real numbers. I can use positives, I can use negatives, I can use 0. All real numbers. The range, that's the y value. Is there any value that I can put in for x that's going to give me a negative value, that's going to give me a negative y? Can you think of any number that I can put in for x where y is going to be a negative number? Yeah, what do you think, Summer?
If it was a negative one.
Yeah, but that's not going to work, is it? No, because that'll just give me a fraction. The answer is, there is no number that you can put in for x. Even if I put in negative 100, all that means is y equals 2 over 1, or 1 over 2 to the 100th power. It's just a fraction. You can never get a negative number, and you can never get 0. So my range is all real numbers. We'll do this, greater than 0. All positive real numbers. Okay? And that's for every, well, for right now anyway, that's for every exponential growth problem. Okay? There's that part of it. Now I've got one more topic here. Some of you guys have seen pictures of my car, okay, on the board. Now this is an example of exponential growth. And let me show you what it is. Let's say that, well, I know when my car was brand new in 1958. Okay, I've looked it up. When my car was brand new, I didn't buy it new. I don't know if I told you the story or not, but I bought it from a used car lot. But when that car was new, it was the most expensive car that Ford made that year. And it was $3,200. Okay? So exponential growth. Let's say that over the years that it grew at 4%. Let's say that it is 4% growth rate, exponential growth, and it grows exponentially. What is it worth today? Okay, so I'm going to give you a formula. And that formula is, and I want to give the same letters that are in the book. And this is real easy. This is just a formula that you plug into your calculator. The cost is equal to A. I don't know why they use the letter A, but that's the original cost of the car, or anything, times 1 plus R raised to the T power. T stands for time. Okay? Everybody with me so far? That's a formula. This is a formula for exponential growth. I'm going to give you 2 examples. Okay. So the cost, A is going to be what it cost originally, $3,200 times 1, and we're going to say it grows at 4%. Well, what is 4%? I can't write 4%. I have to write that as a decimal. What is it? 0.04. All right. Raised to, how many years has it been? 54 years. This is probably not true because I think that's going to be a lot of money. So I go to my calculator, okay, and all I have to do is put in 3,200. I'm going to put in my calculator exactly as it's written on the board. Parentheses, 1 plus 0.04, close your parenthesis. Use the caret key, raised to the 54th power. Okay. So now this car is worth $26,000, we'll say $26,600. Okay.
So you just subtract the time it is now from the time it was back then to get that.
Yes. Sure. That's exactly what you do. Okay? Let me take another problem. All right. I would imagine that most people in this classroom are 14 years old. True? Okay? All right. So if most people in this classroom are 14 years old, let's say that Grandma and Grandpa decided to leave you guys some money. All right. They decided to give you some money, and they gave you $5,000. Maybe your 15th birthday came up, or your 14th birthday, let's say 14, okay? And they gave you $5,000. Now this investor that your parents know say that, okay, well, if you give me that $5,000, I can invest it for you in stocks. And stocks will pay an average of 8%. Okay? So that's going to be our rate. This is going to be the A in our formula, because that's what you start with. The rate is going to be 8%. This is your R. All right. And let's say you want to leave it in there until you retire at, say, I don't know, 62 years old. Okay? So you want to leave it in there until you are 62 years old. And you are 14 now. Okay? How much money will you have at that time? So it kind of hurts right now, doesn't it, to take that $5,000 and just put it away. and not be able to see it. Do you think we're all going to reach 62 years old? Gosh, I hope so. I hope so. Okay, so let's see how much it would be worth then. The total cost then would be 5,000 times 1 plus, not 8, plus 0.08 raised. 62 years old. How much?
48.
48. So we're going to raise that to the 48th power. Okay. So we go to our calculator and we put in 5,000 parentheses 1 plus 0.08, close your parentheses, and raise it to the 48th power. How much money we have from that 5,000? Wow. Wow. When you turn 62 years old, you will have $201,000 and $52.87. Okay?
That's if you don't keep reinvesting the money.
That's if you don't, right. That's if you don't keep reinvesting. That's if you just invest it and leave it. And you know what? I will tell you this. When you turn 62 years old, you're going to look back and say, man, if I just knew then what I know now, I would have all that money. We all say that.
Yeah.
Okay?
They're saying that
All I'm saying is, it's important for you as students. Okay, whether you're 14 years old or whether it's after college and you're 24 and you get a good job, it's important for you to know these numbers. It's important for you to know math. Okay, to know what you can do and to plan ahead. It really is. It makes a big difference. What do you think? You look at the problem before with the car. What do you think made the biggest difference? Is it the amount of money that I invested? I went from $3,200 to $5,000. Is it that, or is it the percentage? What do you think makes the biggest difference? The percentage. The percentage makes the biggest difference. Not the amount of the initial investment. It's that percentage. Okay? So that's how we do those types. And that is all called exponential growth. Exponential growth problems. Okay? Yes?
What if the stock market fails?
Well, you keep reinvesting your money when you.
The thing about this,
You have to be smart. Like, stocks when it
all right, and that's a question I think, nobody can predict the future. And nobody really knows. I mean, yes, it could happen. What I wanted to show you, and the point of this is to show you how exponential growth, something grows very quickly with exponential growth, and that's the point of this. Okay? So, is this a sure thing? No. But it just tells you a little bit about investing. Okay? So, for your homework tonight then, I want you to do on page, let's start on page 524 and 525. And we're going to do problems 4 through 34 even, and problem number 38. Okay, and that will be due on Monday.